Good morning, everybody. I don't see everybody signed on yet. Usually we have a few more than this, but I'm sure within the next minute or so we'll see more and more people. We're starting 4-3, and then again, this is kind of a strange little break for you. You have 2 days off while we have teacher planning days for bringing students back in the classroom next week. And you're definitely going to receive an email from me if you're a distance learner and or a sophomore, because sophomores don't get to come back until March. And watch for that email, because what I'm going to do tomorrow is collate all the rest of the copies for the rest of the year that anybody could possibly need. So when students come back to the classroom next week, they'll get their big pile of stuff just in case, just in case we have to go back to distance learning at some point. And then I want to make sure that that's available to the sophomores and the distance learners as well. So I'm hopeful that I'll have them in door A, that little vestibule inside door A on Friday. But watch for the email. I'll send you a campus email about that. And 4-3, we're not going to go really in depth on 4-3 today, because I do want to save some of that for when we get back in the classroom together after you guys have been gone for 5 days, because President's Day is next Monday. So Pre-Calc 4-3 is trigonometry extended, as we start to learn all of the information that we need to talk about the unit circle and using that. So you want to be able to find trigonometric functions of any angle. We definitely will cover that today. Find trigonometric functions for real numbers. We'll be talking about that today. But describing the periodicity of trigonometric functions and starting our work on the unit circle, we'll wait until after break to come back to that. So, trigonometric functions. Basis of this is we can force our angles onto the x and y Cartesian coordinate plane. So trigonometric functions of any angle will have an initial side, and we've been placing that initial side on the positive x-axis, and an angle that's formed at the center, and then it has a terminal side. So this is our angle, and our angle is made up of different parts of that structure. So we have to identify these using the correct geometry notation. And the initial side and the terminal side are both rays. So the initial side is ray BC, and our ray symbol has to point to the right. And that's because when we make this symbol for a ray, we're saying this starts at B, and then it goes off through C forever. And that's what's happening here. The vertex is the point where the angle is formed, and that's going to be B. We use capital letters to signify those. And then the terminal side would be the other ray, the one where we notice that we have our little arc to show, hey, this is alpha. And that would be ray BA. So it would definitely be wrong to reverse these and say ray CB and ray AB. That's not what's happening here. We have to start with basically the vertex that we see here for B and use those pieces. So that's what makes up an angle. Now, the measure of an angle. That's the number that describes the amount of the rotation from the initial side to the terminal side of the angle. So how much of a circle are we talking about? We know that a full circle is 360 degrees. We know that a full rotation in radians is 2 pi, and that measure of that angle tells us how much. Positive rotations are, of course, counterclockwise, and negative rotations are clockwise. And again, that feels kind of backwards to us, but historically, most of this stuff was written back in Greece, and European stuff always feels a little backwards to us over here in the U.S. So far, just a lot of review here of things we've already talked about. Now, we have to try and place those angles in places that would make more sense mathematically for us. And we like that in the standard position. So the placement of an angle on the xy plane, the Cartesian coordinate plane, so that the initial side is located on our positive x-axis. The vertex is at the origin, and then we don't have control over where the terminal side is. That falls wherever our angle is formed. So we notice in the drawings we have a positive, which is going to be a counterclockwise movement. There's our little arc showing us alpha. And then over in B, we have a negative angle that's going to go clockwise, and that one is beta. So it's two angles in the standard position, with A being our counterclockwise positive measure, and B our clockwise negative. Now, if we have two different angles, and they have the same initial side and terminal side, how does that happen? Well, they could be landing in the same position. If we don't see an arc that tells us how many rotations are taking place, all we know is they land in the same position. And that position is where the terminal side is. And we already have studied that. We know that that could happen. So would their angle measures be the same? Not necessarily. No, not necessarily. We already know this happens when you have angles that are called coterminal. So coterminal angles are angles that land in the same terminal position. That terminal ray is in the exact same spot. And of course the initial is in the same spot, because in standard position we always put those on that positive x-axis. So what this is starting to get to is the fact that for any angle, there are an infinite amount of other angles that hold that same terminal side, because we know that we can find those. And like it says, we have to remember, how do we find angle measures for coterminal angles when they're measured in degrees? So somebody please unmute and remind everybody, what do we do to find coterminal angles if they're in degrees?
Multiply by 180 over pi, or pi over 180 degrees.
Okay, so you're talking about how do we find out what we have in degrees and radians, or what do we have in radians and degrees. This is saying, how do we get those terminal sides to be the same but have two different angle measures?
Add or subtract 360.
Right. We need to add or subtract multiples of 360. Because in order to land in the same place, you'd have to go all the way around the circle. But we can't use 360 degrees when we're studying these in radians, so somebody unmute please and tell us what we have to do to figure it out in radians.
Add or subtract multiples of 2 pi.
Exactly. And just a quick reminder that almost all radians that we're going to work with are fractions, so we'll have to use common denominators to make that happen when we're trying to find those coterminal angles with pi involved. And yeah, I guess it's been a little while since you did your 13.2 worksheet, because that was one of the times when we had to figure out some of those things. So there we are. And as this one is showing, you can have alpha, which is going to be a positive angle because it's counterclockwise, but beta, even though it would be a negative angle because it's going clockwise, that could have the same terminal side, so they are coterminal. And over here, we see two positives, which again, we're just using that add or subtract multiples of 360, add or subtract multiples of 2 pi to land in the same place. So coterminal angles in a positive and a negative angle are coterminal, while both coterminal angles are positive. We can get whatever we need. If they ask us for a positive and a negative, we'll add and subtract multiples of 360 or add and subtract multiples of 2 pi. They just have to tell us what they want. Now, we want to find some coterminal angles, and it says find and draw a positive angle and a negative angle that are coterminal with the given angle. Quite frankly, I think we've done enough drawing. I think we'll just draw the original angle, and then we won't worry about drawing, putting those extra rotations on there for positive and negative angles that are coterminal. So what we would need to do is take our little 30 degrees that we have, notice that it's in degrees, and we could subtract 360 from it and get a negative 330 degrees, or add 360 and get 390 degrees. But let's go ahead and draw that 30-degree angle in standard position. And they didn't really give us a label here, so we'll go ahead and call it theta. And theta equals 30 degrees. So like I said, I think you did enough drawing on the worksheets that we don't need to start putting our arcs all over the place and all of that. But definitely we need to remember that it starts with the initial side on the positive x-axis. Negative 150, well, if we have to figure out a positive and a negative, we'd subtract 360. So we'd get a negative 510. And then we'd add 360. And get a positive 210. And draw the original. And now, yeah, this one I'm going to have to put my arc on there. So negative 150. We know it's going to go past a negative 90. It's not going to quite make it all the way over. And that's because it's a negative 150. So the little piece that we would be missing over there would be another 30 degrees. But I think I'll label this theta equals negative 150 right here. And the reason we'd want to label it something is because really, if we're going to tell them what the coterminal angles are, and we want to use the notation that we have for coterminal, we would put theta, and then we'd have a subscript of COT, and negative 330 degrees, 390 degrees, and for this one, theta coterminal would be negative 510, and 210 degrees. And notice just a comma to break it up there is fine, because it's just a listing. It's a listing of our degrees. And then the last one, which has the 2 pi over 3 radians. I'll start by drawing this one. So I want to remind you, it's written as 2 pi over 3, but we should think of it as 2/3 pi. So all the way across is 1 pi. We don't want to go all the way across. We want to go 2/3 of the way. So that's where our 2 pi over 3 would be. And now to figure out our coterminal angles for this one, we're going to have to think in terms of adding and subtracting 2 pi, but in thirds. So if we have 2 pi, it's 2 pi over 1. We're going to have to multiply our numerator and our denominator by 3 because we need a common denominator of 3. So we'll take 2 pi over 3 and subtract 6 pi over 3. And we would get a negative 4 pi over 3. And then we could take our 2 pi over 3 and add 6 pi over 3. And that would give us 8 pi over 3. So now we could write theta in here, and theta coterminal equals negative 4 pi over 3 and 8 pi over 3. And I use theta because that is the most used Greek symbol that we have for angles, but you could use any of those Greek symbols that we have talked about. You know, the alpha, the beta showed up today already. You could name them phi, whatever you need to do so that you can see those are all going to be coterminal. And like I said, I think if we start putting too many arcs on here, we're going to look back at our notes and go, what on earth were we doing? And we've had enough practice at drawing them, so I don't think we need to go through that again. Now, the quadrants. Remember, the quadrants also go counterclockwise. Quadrant 1, 2, 3, and 4. So notice, labeled in that direction, because we're going to have to start talking about the quadrants and which quadrants is sine positive, which quadrants is it negative in. Same thing for cosine and tangent. So we'll be using that language of the quadrants. Always written in Roman numerals, by the way. Again, that's historic, 1, 2, 3, 4 in Roman numerals. So those are the 4 quadrants of, and like it says, quadrants like Super Bowls are invariably designated by Roman numerals, considering the Super Bowl was just on last weekend. So we need to extend our trig functions so they can apply to any angle. And we'll start in the first quadrant. It's a good place to start. Everything's positive. So investigating first quadrant trigonometry, it says let P, some point, be xy, any point in the first quadrant, and R be the distance from P to the origin. Okay? So somewhere over here, we pick a point xy, and our angle is formed from that little radius that we see right there, and they want us to label that R. Well, we already know that reference angles are supposed to be formed with the positive x-axis. So we would drop our little reference angle down there, and form a right angle. And now I start thinking, well, I already know what I need for the side lengths of this triangle because it went over x and it went up y. And now we have a label for all of those wonderful little sides. Now, it says number 1 is use the acute angle definition of the sine function to prove that the sine of theta is y over r. Well, here's theta. This is our central angle. If I can get my blue marker to turn on. There it goes. Right there. There's theta. And sine of theta, SOHCAHTOA again, is opposite over hypotenuse. So if we look at our little triangle over there, it just makes perfect sense that it would be y over r. Just using our definition of sine. And then number 2 says, well, what about cosine of theta? Well, it's all labeled. All we have to do is come along and say, this is opposite, this is adjacent, and this is hypotenuse. And we can talk about any of those definitions for the 6 trig functions. So cosine of theta, adjacent over hypotenuse, would definitely be x over r. And then number 3 says, what about tangent? Don't forget about the other primary trig function. And we know that as opposite over adjacent. So opposite over adjacent is going to be y over x. So we use that acute angle, like it said in number 1. thought about what we got for sine, cosine, and tangent in 1, 2, and 3. And then number 4 says, well, now finish it up. Express the remaining 3 basic trig functions in terms of x, y, and r. Well, that's not too hard to do. All we have to do is take the reciprocals. So let me extend my page here. And the reciprocal of sine is cosecant. So we're just going to flip y over r and make it r over y. And then we have secant, which is going to be the reciprocal of cosine. So that's going to be r over x. And cotangent, which is, of course, the reciprocal of tangent, which will be x over y. Now, what we're going to cover today, you might not think that these are, incredibly important, that knowing sine is y over r and cosine is x over r and tangent is y over x. But these are really, really important when we start talking about the quadrantal angles. So when we talk about 90 degrees, 180 degrees, 270 degrees, 360 degrees, these are really, really important. If you ever forget them, all you have to do is think about what we did to start this. You could just quick draw a triangle in the first quadrant and use your definitions from SOHCAHTOA to get those. But these are definitely, it's a field called coordinate trigonometry. Coordinate trigonometry. And we have to use coordinate trigonometry for quadrantal angles, which I don't think we'll get to today, but maybe that'll be good anyway because it'll be the first thing that we'll talk about when we come back after your 5 days off. All right, example 2. Evaluating trig functions determined by a point in quadrant 1. Let theta be the acute angle in standard position whose terminal side contains the point 5, 3. Find those 6 trig functions. All right. Notice I'm doing the exact same thing that we did in the exploration. And I know that it's 5 and 3. So then when I see they want me to find the 6 trig functions, I realize I've got to find the other one. I need to know what the other one is. So how do I find the other side? Please unmute and let us know.
Pythagorean theorem.
Yeah, so really quick Pythagorean theorem here. And again, where we would typically take the square root and write a plus or minus, we don't have to do that because this is a triangle and the side length is going to have to be positive. So at this point, it's up to you. You could certainly label this x is 5, y is 3, r is the square root of 34, and you could use the coordinate trig. But I'm thinking at this point, most of you would probably just say, I'm going to use my picture. It's sitting right there. Why would I use coordinate trig for this one? And I'm with you. Coordinate trig, typically I'll save that for the quadrantal angles, the special angles. So, sine of theta. You think about your labels. If I can get my blue marker to be a little faster. There we go. And your SOHCAHTOA. And you realize that's opposite over hypotenuse. Oh, wait, I can't leave that radical in the denominator. And we get 3 square roots of 34 over 34. Cosine of theta. SOHCAHTOA. CAH. Adjacent over hypotenuse. Again, can't leave the radical down there. Like I mentioned before, some of you are probably going directly to this last step now because you've done enough of these that you realize, oh, well, I'm just going to have the square. I'm going to move my denominator into the numerator and then drop the square root symbol for the denominator. Tangent of theta. Opposite over adjacent, 3/5. And then we go to our secondaries. cosecant, secant, and cotangent. And again, this is why you typically at least want to write down that very first step, because that's the one you'll go back to take the reciprocal. So cosecant will be the square root of 34 over 3. Secant, square root of 34 over 5. Yeah, I don't have enough room there for people that are watching this later. That's better. And then cotangent, you flip your 3/5 and make it 5/3. So again, we could have used that new coordinate trig and said, okay, so for sine I need y over r. 3 over the square root of 34. Get exactly the same thing. For cosine I need x over r. 5 over the square root of 34. Exactly the same thing. Tangent, y over x. 3/5. Boom, you've got it. Or you can use your drawing. Either way, at this point, either way is safe. When we get to talking about the quadrantals, we have to do coordinate trig. So use the same definitions for x, y, and r, whether or not x and y are positive, and we can extend our trig functions to any angle in any quadrant. And the question here is, why are we always guaranteed that r will be positive? And we're guaranteed that r will be positive because r is a distance. It's the distance from 0, 0 to the point. And distances are always positive. So your x's and y's might not be. I mean, if they're not in quadrant 1, we're guaranteed we're going to have a negative in front of at least one of them. But r will always be positive. Example 3 says, let's evaluate some trig functions determined by a point. This time we're going to leave quadrant 1. Let theta be any angle in standard position whose terminal side contains the point negative 5, 3, and find the 6 trigonometric functions of theta. Well, let's find negative 5, 3. And we don't have to be real specific. We can just say, hey, it would be negative 5, 3. It'd be up here. But what we need to be able to do is say, well, there's r, and this would be my reference triangle because it has to drop to the closest x-axis. So now it would make sense that the length, not really the length because we're talking about a negative 5, the x-coordinate there would be negative 5, and then our y-coordinate was 3, and we need r again. Well, it's the Pythagorean theorem again, and in fact, whether or not it's going to be a negative 5 or a positive 5, we're going to get the exact same answer. But just so that I'm showing work, for those that aren't necessarily watching right now, we get our square root of 34 again. There's our little angle theta. We can label our sides: opposite, adjacent, hypotenuse, or x is negative 5, y is 3, r is the square root of 34, and use coordinate trig. So this time I think I'll use coordinate trig just to make sure that we get one of those. Sine of theta is y over r. That's going to be 3 over the square root of 34. And again, I'm going to go ahead and jump to, I think you've seen me do enough of that rationalizing the denominator now to realize that that's going to be 3 square roots of 34 over 34. Cosine of theta, x over r, negative 5 over the square root of 34. Sorry, I was already writing the answer. And we at least want that first step so it'll be easier to take the reciprocal. And then Cotangent of theta is y over x. So 3 over -5, -3/5. And then we just have to flip those so that we can give them all 6 of the trig functions. So here's our 3 primaries, and now we need our secondaries. Sine flips to become cosecant. So that will be the square root of 34 over 3. Or you could think of it as r over y. Cosine, flip that and you get secant. Or you could think of it as r over x. It's easiest after you have those basic 3 trig functions, the primaries, to just take the reciprocals. So negative square root of 34 over 5. Cotangent of theta, -5/3. So, see at home, do I really have to memorize cosecant is r over y, secant is going to be r over x, and tangent will be x over y? Most of the time, students memorize the 3 primaries, and then they can just flip them when they need them. And that's because sometimes they're not going to ask us for all 6 of these. They're going to ask us for just the secant, and we have to be able to make our way through that. And like I said, right now we have choices because we definitely like that picture for thinking about SOHCAHTOA, but we also could use the coordinate trig. We will not have that choice when we're talking about the quadrantal angles. So note, there are an infinite number of coterminal angles that share the 6 trig functions above, because we can write an infinite amount of coterminal angles that would land in that same spot. So what that gets to is the point that, yes, there are an infinite amount of trig functions, but there are so many that repeat. That was one of the ways that back when dinosaurs roamed the planet and I was learning trig, we could have tables in the back of our book. We didn't have to have calculators to do that piece because there's only a certain amount of them that are going to be useful. So, our definition of trigonometric functions of any angle. Let theta be any angle in a standard position. Let P be some point xy, any point on the terminal side of the angle, except the origin. And let r denote the distance from that point to the origin. Now, this gives us a little shortcut here, that r equals the square root of x squared plus y squared. But most of the time, we would be drawing our triangle anyway. We're going to draw where everything is, and we'd just use the Pythagorean theorem. But just so you know, it does have its own little formula. R equals the square root of x squared plus y squared. And then we see those coordinate trig formulas. Sine is y over r, cosine is x over r, tangent is y over x. And like I said, usually we just use the reciprocals for cosecant, secant, and cotangent instead of memorizing that cosecant is r over y, secant is x over y, or r over x, sorry, and cotangent is x over y. I got ahead of myself there. So, like it says, what happens when we're not given a point, x, y, to begin with? Because when we started, our objective said, hey, let's find these trig functions for anywhere, any real numbers that we could possibly have. Well, sometimes we can find a point. Sometimes we're going to recognize a relationship and we're going to be able to say, hey, I know that one. And when that happens, that's what we want to use. So we try to find, come on, blue marker, there we go. We try to find an easy point to represent our angle. Doesn't always happen, but it does happen a lot. And that's because we want to focus so much of our energy on those special angles that we know about, the 30, the 60, the 45, and then of course any of those quadrantals. So example 4 says we're going to evaluate the trig functions of 315 degrees. So we want the 6 trig functions for 315 degrees. And if you're looking at that, you're probably saying, That's not a special, Cedarholm. 315? There's nothing special about that. Well, let's draw it, and let's see. All right, so 315, huh? 90, 180, 270. Well, it's not all the way. Well, let's check this out. It's not all the way to 360. Do a little subtraction. Oh, look at that. It's 45 degrees short of all the way around. Well, we know about a special triangle for 45 degrees. We'd put our little reference side right there to form our reference triangle. And we know from the song, and it's hard to start it halfway, but it's 1, 1, square root of 2. Because a 45, 45, 90 is going to be isosceles. And the last thing you want to think is, well, something's got to be negative here because I'm in quadrant 4. Well, it's positive 1, negative 1. And then we have the square root of 2 as the distance from the origin to the point on our triangle. Because it turns out we can pick any point on that R value. I keep wanting to tell you that it's the radius of a circle because we're going to start talking about the unit circle, but we're not quite there yet. And so we want to pick an easy point. And an easy point for us would be 1, negative 1. Again, you have your choice. Do you want to use coordinate trig, the y over r, x over r, and y over x? Or you probably already have the picture drawn, and you just need to start thinking, this is opposite, this is adjacent, and this is hypotenuse. And then you can write down those 3 trig functions. But we can't use theta when we write them down. They actually gave us an angle measure this time. It's 315 degrees. So sine of 315 degrees, cosine of 315 degrees, tangent of 315 degrees, and then we'll take reciprocals. Sine is going to be opposite over hypotenuse, so negative 1 over the square root of 2. And we'd go ahead and rationalize the denominator and get negative square root of 2 over 2. Cosine, adjacent over hypotenuse, 1 over the square root of 2. Again, we'd rationalize the denominator and get the square root of 2 over 2. Tangent, opposite over adjacent, negative 1 over 1, which is, of course, negative 1. And then the secondary trig functions. So cosecant, 315 degrees, secant, 315 degrees, and cotangent of 315 degrees. Go back to the beginning. If we flip negative 1 over the square root of 2, that'll give us the square root of 2 over negative 1, which is negative square root of 2. If we flip the square root of 2 over 1, we'll get the square root of 2. If we flip negative 1, we get negative 1. So at first glance, 315, you think, well, there's nothing special about that. I might have to grab a calculator. But once you figure out with the visual where it lands, then you realize, oh, I have to use a 45, 45, 90. Now let's say you didn't notice that, and you gave me some nasty decimals for all of these. All of them would be wrong. We have to notice those special angles, 30, 45, and 60. That's a must, because again, anytime we can give an elegant and perfect answer, we want to do that. So don't just throw up the calculator right away and say, hey, I'm going to use that for 315. Draw it. You're going to see if there's anything special about it. And if there isn't, well, then, of course, we have a calculator as backup. But we always want to check. So we use this method with both the 45, 45, 90 and the 30, 60, 90 reference triangle situations. Anything special? We need to notice it. So these are the steps to evaluating trig functions of a non-quadrantal angle. So not the 90 degrees, not the 180, not the 270, etc. Draw the angle theta in the standard position, being careful to place the terminal side in the correct quadrant. Number 2, without putting, little tick marks all over the place. You don't have to declare a scale on either axis. Just label your point. They're using P here to stand for point, which is just fine. And like it says, that's going to be on the terminal side of your angle theta. Then, draw that perpendicular so you can get a reference triangle. Once you have that, hopefully you'll see, hey, this is something special. So if this triangle is one of the triangles whose ratios we know, label the sides accordingly. If it's not, then yeah, you have to use a calculator. Number 4, use the sides of the triangle to determine the coordinates of point P, making them positive or negative according to the signs of X and Y in that quadrant. And number 5, use the coordinates of point P and the definitions to determine the 6 trig functions. So notice number 5 doesn't say you will always use coordinate trig, because there's a realization that if we have it drawn, we're probably just going to use SOHCAHTOA to figure out what we have. So, big clue that something nice is supposed to work out is the directions, find the following without a calculator. That is a big hint that we better get a special angle when we do this one. So negative 210. There's our initial side, and we think about negative 210. There's negative 90, negative 180, and then you just ask yourself, well, how much further would I need to go past 180? So basically, you're taking 210 minus 180 in your head to see that that's going to be 30 degrees. Gosh, that's so small. Maybe I'll do this. Put a little arrow there that says 30 degrees. And then you draw your perpendicular so you can form your reference triangle. And you remember, okay, 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2, the other side is the square root of 3. And we, of course, know that that smallest side of 1 is always opposite the 30-degree angle. But I'm not in quadrant 1. So I have to realize that this is actually a negative square root of 3 because I'm going to the left. 1 is positive because I'm going up. And then all they want is sine. So the sine of negative 210 degrees, again, you already have it drawn. You probably would just do SOHCAHTOA, opposite over hypotenuse, and get 1/2. Just ask for 1. Don't have to do all 6. Tangent of 5 pi over 3. I need somebody to unmute and tell me what we should think of 5 pi over 3 as so that we can draw that correctly. Okay, so we'll start there. Then change it into a mixed number, so it'll help you figure out exactly where everything is. So we definitely are going positive on this one. There's 1 pi and 2/3 of the way. Wait, I just feel like that's something I should know. You know, if I went 2/3 of the way, that means there's 1/3 left. Hey, that's 1/3 of pi. Pi over 3, what does that equal in degrees? Well, 180 divided by, oh, it's 60 degrees. So we have another 30, 60, 90 forming there. And again, you have to remember the little song, 30, 60, and 90, it's very easy to see. The short side is 1, the hypotenuse 2, the other side is the square root of 3. So now this time, the 60-degree angle, remember it always has to be opposite the square root of 3, and then our 30-degree angle would be down here, but we don't really care about the 30-degree angle. We're trying to evaluate that 60 degrees right there. And then don't forget to put negatives where they need to be. Fourth quadrant, X is positive because it's going to the right. but y will be negative. And this one was tangent. So for tangent, we need opposite over adjacent. That would be negative square root of 3 over 1, which is just negative square root of 3. So the drawing really helps you think through, hey, how much do I have left here for my reference angle? Alrighty, negative 3 pi over 4. Can somebody unmute, please, and tell me what we should think of that as so we can draw it?
Negative 3 over 4 pi.
Yes, negative 3/4 pi. All right, so I can't go all the way. I'm going 3/4 of the way. Well, then obviously that leaves me with 1/4 of the way. 1/4 pi. Let's see, so that would be 180 divided into fourths. Somebody tell me what that angle is.
45 degrees.
Yeah, 45 degrees. Thank you. All right, I never am good at starting the song halfway through. That's 45, 45, 90. These are easy to name, for it's 1 square root of 2 in the triangle game. Again, let's get our negatives on there. Left, negative. Down, negative. The only thing that's positive is our R value there. And then we're supposed to find secant. Somebody tell me which primary trig function we have to flip to get secant.
Cosine.
Right, and cosine is adjacent over hypotenuse, so we need hypotenuse over adjacent. Square root of 2 divided by negative 1, and we get negative square root of 2. Ta-da! So even if at first glance you're thinking, I don't know what 5 pi over 3 is, I don't know what negative 3 pi over 4 is, remember, if it says without a calculator, and even if it doesn't, draw it first, because you might notice, hey, this is a special one. And those special ones we have to give exact answers for. No nasty decimals off of our graphing calculator. So angles whose terminal sides lie along one of the coordinate axes, those are problems. And that's because you can't form a reference triangle. I mean, if my angle is 0 degrees, 90 degrees, 180 degrees, or 270 degrees, I've got trouble. I can't draw a reference triangle. Well, that's why these are the special ones, and they're called those quadrantal angles. These are the ones we definitely have to use coordinate trig for. So this is where we have to know y over r, x over r, y over x. So for these angles, we cannot produce reference triangles. But it becomes really super easy to pick a point P along one of those axes. And that is where we're going to stop, because I definitely want to talk about those quadrantals when we get back after your 5 days off. So we hit those two parts of the objective pretty doggone hard. And I didn't get a chance to look at this. I'm hoping that's something you can feel like, hey, I already know how to do all of this. I know we rewrote it. Let me take a quick peek and make sure. But as you know, always, if you're doing a homework assignment and you're thinking, I don't think we covered this yet, well, then just stop and wait. Yep, you will be able to do all of these without any trouble. Although I guess I'm telling 3 people at this point. Have a great day, everybody.